is the wonderful Thea Flowers. I'm thirsty. And that too. Okay. It's alive. That's a good sign. Out of curiosity, how many of you actually read the description of the meetup event today? Okay. How many of you didn't? Okay, y'all are gonna have no idea what's about to go down.
You mean like in its entirety?
That person is canceled.
Not the first time today.
Cool. So, as Alan mentioned, I am Thea Flowers. Am I sure? I am? Okay, cool. Things are working. This is new. The last time that I spoke at Puppy, I bombed so hard that I changed my name. That's not a joke. So, today I'm going to talk to you all about a really fun project that I've been working on over the last year or so. I'm going to talk about building a synthesizer inspired by the Sega Genesis. Another show of hands. How many of you know what a synthesizer is? Okay, good, that's good. Because this was going to get really messy if you didn't. How many of you know what the Sega Genesis is? All right. My kind of people. We're all best friends now? So, yeah. So in this talk, I'm going to share with you what makes the sound of the Sega Genesis special to me. And I'm going to talk to you about what it takes to build a synthesizer using the sound chip from the Sega Genesis. And then, if the demo gods shine upon us, I will actually give you a nice little demo of what it sounds like. So I'm going to throw a lot at you really fast. Strap in. It's going to get a little wild. My purpose here tonight isn't to teach you everything it took for me to build this synthesizer. It took me the greater part of a year, so I don't expect you to get it all in 30 minutes. What I want to do is show you that a silly software engineer like me that knows absolutely nothing about hardware and didn't even go to college can build hardware and do amazing things with it. So I hope that happens. So let's talk about what makes the Sega Genesis special to me. I remember being a young kid and going over to my cousin's house, because I have a billion cousins. And they had a Sega Genesis. It was like a mind-blowing thing to little me, right? To see all these lights and sounds and speed, and just really being like enthralled into this thing that I've never seen before. These are some of the earliest memories I have of playing video games, and they stuck with me throughout my entire life. They are what inspired me to become a programmer, to become a software engineer. And while I never got around to making video games, they still sort of permeate everything that I do. So I wanted to make a synthesizer with that inspiration. And it takes a lot of inspiration for you to do something new like this and actually finish it. So that's like the biggest thing you need. A lot of people ask me, where do you even start? You start by being inspired, and really hard-headed. So let's talk about what makes the Sega Genesis sound unique. And really, what makes video game music sound unique at all, right? Well, a little bit of history here. Early video game consoles were under a lot of constraints. These were effectively 8 or 16-bit computers. By comparison, the computers you have today, even the one in your pocket, is 64 bits. They had limited resources across every axis: CPU speed, RAM, storage, everything. They couldn't just play back music recordings like we do today. For comparison, an MP3 is about 4 megabytes in size for a 3.5-minute song. A NES game is about 128 kilobytes. That's all the space it had. You couldn't just put MP3s in there. Also, there's the fact that MP3 wasn't invented until 1993. So there were problems. So there's a clever engineering solution here. Instead of recording music ahead of time and then putting the recording onto the cartridge, what they would do is they would put the sheet music, so to speak, and they would have the hardware synthesize it in real time, which is really, really cool. Compared to an audio recording, the score or sheet music is much, much smaller. So that's what these early video game consoles did, and it's what the Sega Genesis did. Before the Genesis, these consoles in the late 70s and early 80s generally used pretty limited hardware to do the actual synthesis part. These were called programmable sound generators, or PSGs. They had extremely limited capabilities. They could generally do about 2 to 5 sounds, or channels, of square, triangle, and noise. And this is what those look like if you have an iPad and you draw them out. This would be like. But I actually want to show you what they sound like. Sound is much more important to me than that. And fingers crossed that my sound works. It's just muted. Okay, hold on. Might have to. Okay, yeah, I think this is right. Okay. All right. Everyone knows that song, right? Okay, cool. I grew up with that saying nursery rhyme for me. This is a classic example of the PSG sound. This is the Super Mario Brothers theme for those of you who don't know. Today you learned. Despite the extremely limited hardware, the very clever sound programmers were able to create an iconic and memorable theme. And if you listen to this, you can actually hear that the melody is a square wave, the bass is a triangle wave, and the drums, like the hi-hat hit, is a noise wave. So I'm going to play that for you one more time. Take a little listen. I lied, apparently. There we go. So that's really all the PSG could do. That was it. That's all you had. That's why every NES game sounds like they're played by the same band. So what Sega wanted to do was to beat Nintendo. So they said, we're not going to do that. We're going to do something really cool. They decided to implement a method of sound synthesis that was very, very popular in the mid to late 80s with pop music. It's called frequency modulation synthesis. It's mind-blowing, basically. Instead of having 4 unique sounds that you could use, you have, or 3, you have thousands of unique sounds. And it's really, really awesome. So, Sega contracted the world's greatest jet ski / motorcycle / piano company, Yamaha, to create the sound chip for the Sega Genesis. Yamaha came back with a cost-reduced, feature-limited version of the same sound chip that they used in their legendary Yamaha DX7 synthesizer, which you can hear on tracks like Take On Me, Danger Zone, and thousands of others. It's legitimately everywhere, especially in the 80s. Like you would trip and fall into a pile of DX7s. Tragic. So even though it was limited compared to its bigger sisters, it was still a hugely powerful thing to include in the Sega Genesis. It had 6 channels, so you could have 6 different things going on at once. We'll get into what FM operators are later, but it had 4 compared to the DX7's 10. So it had, not as many, but it still had enough to do its job. And it just sounds miles ahead of everything that came before it. And I know that here in 2019, this is going to sound dated, but this blew people's minds when they heard it back in '89. So I'm going to play you a song that was written for the YM2612 and the Sega Genesis, and it's going to be awesome. In that one track, we heard, I think it's 10 different unique instruments, which is pretty cool. Of course, it would swap channels out so you hear different instruments in different parts, but this is huge. Game audio sounded alive and real for the first time. So, that's what the Genesis did. So, the Genesis didn't keep the spotlight for long, of course. The wheel of fate happens. Nintendo dropped the SNES, and it included what's called a sampler, which lets you synthesize music using tiny clips from real instruments. So that increased the fidelity even more. And then the PlayStation came along and just ruined everything. It brought CD playback, which meant that we could just play back recorded audio, and it was basically game over. Sound hardware was irrelevant. So the Genesis really happened in this special kind of moment in history where it made sense to include powerful sound synthesis hardware directly in the console. And that's what gives it such a unique and special voice. All right, cool. So hopefully I've convinced you now that Genesis is rad, and that all music should be made using FM synthesis if at all possible. So let's talk about this weird way of making music, right? What is FM synthesis? That's a deep question, and we don't have time to unpack all of that. But I'm going to show you a little bit of how it works. To do that, we're going to look at subtractive synthesis first. It's a different way, but it's a lot easier to understand. So don't worry if all this overwhelms you. I'm going to show you a visual and an audio sample here, so I don't know the word for that. And it's going to hopefully help you grasp it a little bit more. But subtractive synthesis uses harmonically rich oscillators like a square wave, a triangle wave, or a sonic wave. And then it uses filtering to remove harmonics and shape that sound. Again, let's just look at it. It's much easier if we look at it. On the left here is going to be called what's the time domain. It's going to show you a slice of the wave, so just one cycle of the wave. And it's going to look like square at first, because it's a square wave. And then on the right is the frequency domain. This is going to show you the harmonic content. So watch it, and over time I'm going to add more and more filtering. So what's going to happen is the wave is going to change shape, and the harmonic content is going to go down. And due to a neat trick about how our ears work, it's going to sound quieter over time. And that's not because I'm turning the volume down, it's just because our ears perceive less harmonic content as less loudness. So, let's listen to it. Cool, that was your free hearing test. You all passed. Yeah, so that's how subtractive synthesis works. FM synthesis is weird. It works the other way around, and that's mind-bending. It uses harmonically simple sine waves. Sine waves basically have just one piece of harmonic content, which is called the fundamental. It then uses modulation to introduce harmonic content. It basically wiggles the wave around really fast until it looks different. It's basically magic. It has a much higher learning curve, because it's harder to wrap your head around. But let's take a look at what it looks like. This is going to be the same setup. Left, time domain, right, frequency domain. And we're going to start with a super simple wave. And you're going to notice the harmonic content increase as modulation increases over time. So take a look at this. It's going to get weird. So I was increasing the modulation in like steps there, so like that's why it's so jumpy. But yeah, so it's a little bit different. So the way FM synthesis works is it has all of these different sine waves moving each other around, and the operators is how many of those different sine waves you have to play with. So the Sega Genesis has 4, so you have 4 different things that you can arrange in different ways to wiggle each other around and they make sound. It's basically magic. So it turns out that there is mathematical proof that a complex FM synthesizer can approximate any sound. Given enough operators, you can make anything sound like anything. The DX7 can get a lot closer than the Sega Genesis can. It has 10 operators to play with. The Sega Genesis only has 4, so it sounds a little off, but it sounds unique, which is lovely, right? Yeah. So now you're all experts on theory. And I expect you all to go build FM synthesizers now. But the good news is that we have the sound chip. We don't have to know all the theory. We should know how to talk to the sound chip. Let's let the sound chip do everything. Let's build a synthesizer, right? Here's what I want to build. This is a poorly drawn picture of a keyboard, a PC, and a synthesizer. What I want to do is I want to have my MIDI keyboard, this thing, talk to my PC. So MIDI is the way that audio equipment sends control signals to each other, basically. It's a simplified explanation, but it's good enough for our purposes. So the MIDI keyboard sends like note on, note off data to the computer. The computer then routes that data out to the synthesizer. The synthesizer uses that data to actually create audio, so that when I press a key, it makes things happen. Yay! Now, how do we get there? So digging a little bit into the synthesizer part of things, right? This guy. This is a block diagram of what goes into the actual synthesizer. So what we got here is we're going to be talking over USB. So we're still going to be talking MIDI. MIDI is the protocol, USB is the transport. And this will be talking to a microcontroller. That's what UC stands for, microcontroller. That microcontroller is going to take those MIDI messages, and it's going to translate it into stuff that the YM2612, the sound chip from the Sega Genesis, can understand. And then the YM2612 is going to send audio to an audio amplifier, and it's going to go out. And I can use that audio to record things or to play it through speakers that we're doing here tonight. Cool, cool. All right. So the tricky part then is talking to the sound chip. How does the YM2612 actually work? Well, it functionally acts as a big RAM chip. Or, if you'd like to, you can think about it as a big array. It's an array of bytes. So you have an array index, an address, and you have an array value, which is the value of the register, basically. And changing these bytes in this array causes the synthesizer to do different things. You can control how it sounds, you can control whether or not a key is on or off, all kinds of cool stuff. So our microcontroller has to basically write to this RAM chip or write to this big array in memory, and the chip will do the rest, which is great. Pretty hands-off, easy, right? No, it's not easy. It's very hard. So our first step in designing hardware is to make a proof of concept. Will this even work? Is this even possible? So MIDI is hard, and figuring out how to translate from MIDI to YM2612 is even harder. So what we're going to do for our proof of concept is just play back some pre-recorded stuff. And there's a file format for that called VGM. VGM stands for video game music, which is a misnomer, because it only really works for Sega stuff. And so it's from an alternate universe where Sega won. And I like that idea. Anyways, a VGM file is basically a dump of all the commands from the CPU to the YM2612. If you ever use Chrome DevTools and use the record HB thing, it's kind of like that. It's very opaque. Our microcontroller doesn't have to know anything about it other than just like, I got a command to write to the YM2612. I'm going to write to this address, and I'm going to write this value. And it's that over and over again. That's it. Super simple file, basically. So this is great. We don't have to actually understand anything about the YM2612 to talk to it. So here's the proof of concept. It is an Arduino plugged into right up to the YM2612. And it's playing back a very short VGM file. So let's listen. Look at it go! That was legitimately, that's a video the first time I ever had any sound coming out of the thing. And I think as soon as I hit stop recording, I went, yes! Yes! Maybe it's in the video and I just cut it off. So great, we're done, right? No, we're not done. You have to go to the next step of hardware design, which is prototyping. With prototyping, what you want to do is move from your early sort of rough, does this even work, to like kind of getting close to the final components of things, right? So for my prototype, I put everything on a breadboard, which is this thing. You can't eat them. I asked. Breadboards let you move things around easily because you don't have to actually solder them down. And then, so up here at the top left, that's the microcontroller. That's called a Teensy. It's like an Arduino, but it's much faster and better. Next to that is the YM2612. So, and the yellow lines are data bus, and the blue lines are the address bus. There's a screen at the bottom that says Nintendo, don't try that at home. And then on the bottom right is a headphone amplifier to amplify the audio coming out of the chip. So these are basically all the components we saw in the block diagram earlier. Yay. Got it plugged up, got it all working, and it plays back music. Awesome. So this is still VGM playback. I'm not controlling this with MIDI on the keyboard right now, but it works. That's rad. So we're done, right? No, this is actually where I ran into my first real challenge. Audio is really noisy. So when I gave a practice notice talk, someone was like, what is audio noise? Have you ever tried to tune a radio? I know this is like a super dated reference. try to tune a radio and you're like in between channels, it's like that. It's like, it's terrible. Basically, it's this unintentional background garbage that drowns out the actual signal of what you want to hear. This synthesizer is live right now. You cannot hear it. If I turn it way up, you'll hear a little bit of noise. But before, it was like bad. So we got to fix that. It's a hard yikes. How do we reduce noise? Well, I did some research, and it turns out the YM2612 is weird. Who would have thought? It turns out the audio coming out of that thing is really low compared to modern standards. And that headphone amplifier I had was expecting modern standards. So I was like, I don't know what to do with this. So the fix is to use a proper audio amplification circuit that can deal with that rather odd audio output. So I did what you should all do when you don't know what to do: research. I did some research and I found a really excellent modification for the Genesis itself called the Mega Amp. It's just a lovely name. It uses modern audio grade components to create this crystal clear audio output from the console itself. This is what the schematic looks like. Don't worry if you can't read the schematics, neither can I. I modified that and made it work standalone outside of the console and used that as the audio amplifying board for my synthesizer. Easy, right? No! None of this is easy. The answer is always no. It turns out this is hard. So this is the first time I got it to work. This is on a proto board. This is the third attempt. And I did this after crying about it for an hour. And then it worked, and I was like, someone felt pity for me. And this is a proto board. It's like a breadboard, but you solder things down, so it's permanent. And a lot of hobby projects will use proto boards just as the finished project. Cool. I moved everything else to proto boards too, so like, nice. Or at least I thought at the time. So, noise is gone, right? We finished it. It's done. No! It turns out the things are less noisy, but still like unbearably noisy. So, I did what you should all do when you don't know what to do: research. It turns out that there's a lot of things that can introduce noise, especially into audio circuits. They're very fussy. So, the breadboards and the protoboards can basically, they act like little antennas, and they just pick up electromagnetic interference all over the place, like a poorly tuned FM radio. The power supply can also introduce noise into audio circuits because power supplies tend to like wiggle around a little bit. They're not consistent. And the more they wiggle around, or the higher frequency they wiggle around, it can cause all kinds of weird stuff to happen. So USB is not very clean in terms of power supplies. And it turns out that teensy, the microcontroller, and the display also do bad things to the power supply. So we have to fix all those. So based on my research, I figured there were two things I could do to fix this. I could use a separate external power supply. So I'm using a 9-volt power supply. It's right here. That thing. To power the thing. So it talks USB, but it doesn't use USB power. And I have like separate regulators for the teensy and the display, and then a separate regulator for the audio board. So that's good. They're well isolated from each other now. That's good. The other thing was to eliminate the proto boards, the very substrate on which I built my kingdom. Wait, how do you do that, right? Well, you learn how to make printed circuit boards, of course. As a hobbyist, that seemed insurmountable. I was like, I don't know anything. I can barely read schematics. How am I going to do that? Well, it turns out there's really excellent free software, and there's extremely cheap prototyping services out there, and you can make it happen. I watched a video series from DigiKey on how to use KeyCAD, which is a software design tool for schematics and PCBs. I printed everything out on paper and checked the component sizes because I'm like, I only wanted to order this once because I didn't know how much it would cost at first. I heard it was cheap, but I didn't actually go look. And it ended up costing me $21, so I could have done way less thinking about it. This is the motherboard of the synthesizer designed in KeyCAD. And on the left is the teensy. On the bottom right there is the YM2612, and at the top is the power supply section. And then here's all three boards, fresh from PCBWay. And that's the front and back of the board, so that's why there's 6 of those. So the display and button board is on the left, the motherboard is in the middle, and the audio amplifier is on the right. So yeah, then you just gotta put it together. Woo! It worked the first time, which is an absolute miracle. If you do this, expect your first PCB to not work. Because subsequent projects did not work. And then I laser cut a nice acrylic case for it. So, rad. That's the final hardware. That is this one, right here. They're one and the same. Okay, so this whole time I've just ignored software. Which is a hilarious thing to do. There's software to that. Up until now, I've showed VG and playback, but that's not what I wanted when I set it out. I wanted to not just play back existing songs. I wanted to be able to compose my own songs using the YM2612 and hit buttons and have noise happen. So, as I mentioned earlier, MIDI is the way things talk. So, we had to teach the Teamsy how to turn MIDI into things that the YM2612, the sound chip, understands. The problem is, though, the YM2612 is undocumented, because why would it be documented? Not even Yamaha themselves. Apparently they're too busy making jet skis to write documentation. I emailed them, that's what they said. So we turned to reverse engineering. Easy, right? No! Thankfully, I didn't have to do much. Most of the secrets here have been discovered by others. The most comprehensive resources available are websites that tell you how to write homebrew for the Sega Genesis, and emulator source codes, because they have to actually implement the YM2612, so you can go peek inside how they're emulating it. Those are great if you're like writing software for the Sega Genesis or writing an emulator. They're not as good if you're trying to like actually interface with real hardware, because they make a lot of assumptions about hardware that aren't true. So what we can do is, I mentioned that the YM2612 is part of a bigger family of chips. So we can go look at the manuals from its sister chips, because they have similar electrical and timing characteristics. The problem is that Yamaha is also too busy making pianos to write their manuals in English. I don't know Japanese. I'm a white girl from the South. We barely had Spanish in school. So, I don't know any Japanese. So trial and error, right? I do have some friends that know Japanese, and they help me out a little bit. But really, a lot of it came down to guesswork. I like legitimately had a little button I would press to make the delays longer and longer between write cycles. And then when it started working, it's like, all right, that's the right value. Good to go. So, fine, whatever. I'm gonna skip that video. So, of course, the synth needs to do more than make noise. There was so much more involved in writing the software that I wish I could go into here. But really the hardest part was talking to the YM2612. Everything else built on top of that. Everything from parameter editing to patch loading and saving to the UI. There's an actual UI on this thing. That all took time as well. But none of it was hard compared to talking to the YM2612. So this brings us to today, to here and now. This is upside down, is the completed synthesizer. It works. So how about we make some music together? Yeah. I'm glad you're excited. I'm nervous. Okay. All right, I'm just gonna show you. I'm just gonna play some sounds for you to start with. All right. So because the Genesis, the synthesizer here, has 6 voices, we can play 6 notes at a time. That means we can do cool stuff like. We can't play more than that. Denied. But that's more than enough to work with. It can sound all kinds of different ways. So some of you might have heard, if you came early, I was testing things out, and you can play Zelda music. But that's not all. Like, if you want to get real Castlevania about it, yeah, we can get real Castlevania. I like that. It's like a really intense. It's gritty. And, you know, there's all kinds of other cool stuff in here. This is supposed to be a piano patch. As you can hear, this synthesizer's not good at approximating a piano. But it can also make like totally unique, weird sounds, like this one. What instrument is that supposed to be, friends? I don't know. I have a patch randomizer, and that was what that came up. But let's make some actual music with it. Yeah. So, okay. I have a dope beat. By dope beat, I mean I have some really simple drums going on here. Let's listen to my really simple drum beat. Simple. Yeah, it's a good groove for him. Alan likes it. And his is the only opinion that matters. So, for my dope beat, let's add some bass. I want some chunky bass. That's chunky. That's chunkier. Rad. All right. Fingers crossed that I don't screw this up, but if I do, I have a pre-recorded track, so. Let's throw some bass on these drums. Dope beat. But we can't make a song with just drum and bass. There's not like there's an entire genre dedicated to that. Is there? We need some like real cool chords to go into. We'll load a different patch. We're gonna hear some dope chords, or some chill chords, sorry. Beautiful. It's like soulful almost. I like it. What do y'all think? All right. That's not what I would actually play though. Be for real. This is all one great direction. Hold on. So let's throw some chords on this. Alright, don't give it away for your friends that are still behind. Needs a melody. Something strong and memorable that you would send to your friends without prompting. It's almost there. That's closer. All right, let's make work with that. Let's do it. All right, I have to know, who doesn't know what song I'm playing?
Does it count if you don't watch the video though?
That person is canceled. Because I watch Never Gonna Give You Up all the way through every time. So the audience that doesn't know this song. You have just been rickrolled. And all of this was an elaborate ruse to rickroll an entire audience. And you all fell for it. Oh my God. Thank you all so much. Inspired you to make some hardware, even if you are only a software person. I hope this has encouraged you to make some music in your tone deaf. Make good art. Make music. Make hardware. Make software. Put it all together, and you make something as ridiculous as this, and you can rickroll an entire audience. All of this that I showed you is open source. The hardware design, the software, everything. I don't sell these. If you want to buy one of these things, I have a friend named Casser who makes similar hardware that you can buy. You can find me at all these places. Please don't tweet mean things at me, but you can tweet nice things at me. I will be around afterwards if you want to ask me questions and stuff. I also want to give a special thanks to Benny, who did the sound stuff. Without him, you could not have been rickrolled. If you can blame anyone, blame him. I also want to thank Alan and also all the puppy volunteers and the host, Carveth, for having me and letting me do something this ridiculous at your meetup. Thanks. Bye.
Thea did tell me she was going to rickroll everyone, and then
nothing to stop it.
And then I forgot. So I also just got rickrolled. So I also am part of the joke. So I feel just as bad as everyone else, if not worse. I could have prevented getting rickrolled, but I danced to it. So oh well. Anyway, thank you everyone for coming out tonight. It's been a wonderful, successful meetup as always. We're going to do this next month as well, and the month after that, and the month after that, and the month after that. Don't forget that Pi Cascades has their CFP open, and you should submit all of the talks. We have speaker mentors if you need it. First-time speakers are not only welcome, but absolutely encouraged. If you have any questions, ask me or Thea. We still volunteer and help out with Pi Cascades. Other than that, thanks everyone for coming out tonight. The after party is at Fido. It's like right there. Yeah. Thank you. Have a good one.